In order to better understand our digital systems and circuits, we're going to need to understand some basic abstract algebra. And we're going to start by looking at Euclid's division theorem. So let Z be the set of integers, so n belongs to Z means that n is an integer. The theorem here says that let n be an integer and d a positive integer, then there exist two unique integers q and r such that n equals q times d plus r, and r is larger than or equal to 0 and less than d. We're going to call q the quotient, r the remainder, and d the divisor. The remainder is now written as r sub d of n, and you can say that this is just the remainder when n is divided by d. This is also equivalent to writing n mod d or n modulo d. So let's look at a few different examples of this. So what we want to do is that we want to write n equals q times d plus r such that r is larger than or equal to 0 and less than d. The first example, we have n equals 43 and d equals 8. So if we divide 43 by 8 and then we round this down, we will get 5. So this means that we can write 43 minus 5 times 8 equals 3. And writing this in the form that we are looking for, we can write it as 43 equals 5 times 8 plus 3. So 43 is here our n, 5 is our quotient, 8 is our divisor, and 3 is our remainder. So we have n equals q times d plus r. And this can also be written as r sub 8 of 43 equals 3. So the remainder when 43 is divided by 8. In another example where we have n equals negative 43 and d equals again 8, we can do in a similar way. So we can write minus 43 divided by 8 and we round this down and this will give us 6. So we can write minus 43 minus 6 times 8 equals 5, which will give us minus 43 equals minus 6 times 8 plus 5. So again here we have n, we have the quotient which is minus 6, and we have the divisor which is 8 and the remainder which is 5. So we can also write this as the remainder when we divide minus 43 by 8, this will equal to 5. In our final example, we're going to use n equals 24 and d equals 4. So here we can write 24 divided by 4 and then we round this downwards and this will equal to 6. So here we can write 24 equals 6 times 4 plus 0. So the remainder when we divide 24 by 4 equals 0. So in this case we say that 4 divides 24. So 4 divides 24. We write it like this. For the remainder we have the following property. So for all choices of the integers n, I, and d, the remainder when we divide n plus id by d is the same as the remainder when we divide n by d. We can prove this as follows. So what we have from the beginning is that we can write n equals q d plus r. So if we start by the right hand side, we can write this as the remainder when we divide n by d. We can write this as the remainder when we divide q d plus r by d, and this by definition is r. Looking at the left hand side, we can expand this as well, so we can write n plus id. We can write this as, so instead of n we use what we had before, qd plus r, and then we still have plus id. Now what we do is that we collect all our d's, so we have q plus I times d plus r. But if we look what we have here, this is actually what we can see is that q plus I, we can write this just as q prime. So this says that we have n equals q prime d plus r, and the remainder here is the same. So this is still r.